Good afternoon, children. Welcome to our chemistry online class. So we reached end of our chapter. Last class we have discussed about alkynes. Today we are going to discuss about aromatic hydrocarbons. Hydrocarbons also exist in the ring form. That is known as aromatic hydrocarbons. We will see what are aromatic hydrocarbons. These hydrocarbons are also known as arenes. Why they are known as arenes? Because they possess pleasant odor. That is aroma. This aroma means pleasant smelling. That's why they are named as aromatic compounds. The parent member of the family is benzene. We know benzene having molecular formula C6H6 and it is a hexagonal ring, that is it contains 6 carbon atom and 6 hydrogen atom and the alternative double bond in the structure. To check here you can see alternate double bond, that is if one double bond in one position, the next double bond will be in 3. Next will be in the 5th position. So an alternating double bond also present in aromatic hydrocarbon, that is benzene. And aromatic compounds containing benzene ring are known as benzenoids. For example, benzene, toluene, naphthalene, etc. And which is not containing benzene ring are known as non-benzenoid hydrocarbons. We'll see what is the resonance structure of benzene. If we check the stability of benzene, it is very highly stabilized compound. Its stability is due to resonance. We can explain its resonance by its structure. In 1865, Kekulé, he is a scientist, gave a ring structure for benzene. And in that, he could not explain the 3 double bonds. He couldn't able to fix the double bond. Where will be the position of the double bonds? And later he suggested that double bond keep on changing their position, and this is called resonance. So the changing of double bond is known as resonance. And this resonance structure supported by the following facts. Because if you check the carbon-carbon bond length, that is a sigma bond, that is 139 picometer, which is intermediate between bond length of CC bond and C double bond C bond. So it is in between. So it is changing. And due to the resonance, the pi electron charge in benzene gets distributed over greater area. That is, it gets delocalized. That is, it continuously moving. As a result of delocalization, the energy of the resonance hybrid decreases. And according to the orbital concept, each carbon atom in benzene is sp2 hybridized. Each carbon atom is sp2 hybridized. And one orbital remains unhybridized. Out of the 3 hybrid orbitals, 2 overlap axially, that is sigma bond. With the orbitals of the neighboring carbon atoms on both sides to form sigma bond. So this is the sigma bond, axial bond, and the third hybridized orbital of the carbon atom overlaps with the half-filled orbitals of the hydrogen atom, which result the CH bond. Thus, benzene has a planar structure with bond angle 120 degree. There is still one unhybridized 2p orbital which overlaps sidewise with a similar orbital and show pi bond. As a result, the electron orbital cloud is spread all over the 6 carbon atom. So it's all over the carbon atom. There are two continuous rings of pi electron clouds, one above and the other below, and plane of the carbon atom shown like this. Aromaticity. Aromatic compounds are those which resembles benzene in chemical behavior. These compounds contain alternating double bond and single bonds in a cyclic structure. They undergo substitution reaction rather than addition. This characteristic behavior is called aromaticity. The aromaticity can be defined as similar to behavior of benzene and which contain alternate double bond and single bonds, and they have cyclic structure. They undergo substitution reaction rather than addition. And the aromaticity depends on the electronic structure of the molecule. If we are saying a compound is aromatic in nature, it should be follow certain factors. First one is contain a cyclic cloud of delocalized. Next one is planarity. For the delocalization of the pi electron, the ring must be planar to allow cyclic overlap of p orbitals. That is, the compound should be planar. Ring must be planar. And 4n plus 2 electron rule. 4n plus 2 pi electron rule. For aromaticity, the pi electrons cloud must contain total 4n plus 2 electrons, where n is an integer equal to 0, 1, 2, 3. This is known as Huckel's rule or aromaticity rule. For example, benzene contains 6 electrons. That is n equal to 1. That is in the formula 4n plus 2 pi. For example, 4 into 1 plus 2. 3, 12. Four n plus 2 rule. So, 4 into 1 plus 2. This contains 6 electron. We know 6 electron. If we take naphthalene, if n equal to 2, it contains 10 electron. Similar to anthracene, it is also contain 4 pi electron. If we check the structure of benzene, here 2 electron, here 2 electron, here 2 electron. So it is a aromatic compound. Preparation of benzene. First method is decarboxylation of aromatic acid. It's a laboratory method. That is heating sodium benzoate with sodium hydroxide. In the presence of calcium oxide, we will get benzene. Reduction of phenol. We know phenol is the compound which contains benzene ring with OH. It is distillation with zinc. We will get benzene. We'll see what are the properties of benzene. Physical properties. Benzene and its containing up to 8 carbon atoms are colorless liquids with the characteristic smell. Aromatic hydrocarbons are immiscible with water but are soluble in organic solvents. They are inflammable and burn with a sooty flame. Sooty flame means black color flame. They are toxic and carcinogenic in nature. It is a toxic compound. The melting and boiling point of aromatic hydrocarbon increase with increasing molecular mass. This is due to increase in the magnitude of van der Waals forces of attraction, which increases molecular size amongst the isomeric agents. Para-isomer has highest melting point because it is having more symmetrical structure. If compared to ortho and meta position, para-isomers having high melting and boiling. For example, if we draw a compound, this position is known as ortho position, and this position is meta. This position is para. So if we cut here, two sides are equal in nature. That is known as para position. It is more symmetrical. But if we cut here, it is not symmetrical in nature. If If we cut here also, it is not symmetrical in nature. But in the para position only, the compound will be symmetrical. So, para position having highest melting and boiling point compared to ortho and meta position. We'll see the chemical properties. We know aromatic compounds will undergo electrophilic substitution reaction more, and we'll see the mechanism of electrophilic substitution and addition reaction. First one is nitration. That is, the replacement of hydrogen occurs in the ring and nitro group, that is NO2 group, is added. This is known as nitration. So, benzene is heated with concentrated HNO3 and H2SO4 about 330 Kelvin. We will get nitrobenzene. Next one is halogenation. That is replacement of hydrogen atom in the ring by halogen. Halogen means any halogens. This method is known as halogenation, that is addition of halogens. So, arenes react with the halogens in the presence of Lewis acid. FeCl3, FeBr3, LCl3, these are Lewis acid. We will get halogen containing compound, for example, chlorobenzene. Sulfonation, replacement of hydrogen atom with the sulfonic acid. So, benzene is treated with fuming sulfuric acid. We will get benzene sulfonic acid. Next one is Friedel-Crafts alkylation. Alkyl group means R group, that is either CH3, C2H5, C3, H8 or H7. These are alkyl groups. So, with benzene is treated with an alkyl halide in the presence of anhydrous aluminum chloride, we will get alkyl benzene. So, from this halide, this alkyl group, which will add to the benzene. So, we are adding alkyl group. So, that's why it is known as alkylation. It is identified by the scientist Friedel-Crafts. That's why it is known as Friedel-Crafts alkylation. And next one is Friedel-Crafts acylation. This is also similar. Acyl group is this one, CH3CO. So, instead of alkyl group, if acyl group is added to the compound, then we can call it as acylation. So, these are all electrophilic substitution reaction. So, according to experimental evidences, substitution, that is electrophilic substitution reaction, is supposed to proceed via the following 3 steps. There are 3 steps. First step is generation of the electrophile, formation of carbocation intermediate, removal of proton from the carbonation. So, we will see the first step, generation of electrophile. We know in the reaction we are using anhydrous AlCl3. It's a Lewis acid, and here it is used as a catalyst. So, the attacking reagent may not be strong electrophile. Therefore, first all an electrophile is generated by the preliminary reaction. For example, during chlorination of benzene, an electrophile Cl plus is our electrophile is generated by reacting with the anhydrous Cl3. So, chlorine is reacted with AlCl3, which produce Cl plus and AlCl4 minus. So, this Cl plus is our electrophile. Second step is formation of carbocation or arenium ion. So, the electrophile approaches the pi electron cloud of the aromatic ring. So, here you can see the benzene. Here will be the pi electron. So, electrophile reaches the pi electron. So, it creates, so this electron having negative charge. So, it will attract to the electrophile. So, which create a positive charge in the ring. So, it's helped to form a sigma bond. The next step is the arenium ion gets stabilized by the resonance. That is, this positive, this arenium ion will shift here. Like that manner it will stabilized. So, the resulting carbocation has 3 important contributors such as 1, 2, 3 structures are there. So, it will delocalized. Step 3 is removal of proton. So, here you can see the proton. So, it will remove. So the carbocation form loses a proton to the nucleophile present in the reaction mixture to the form substitution product. We know the first step there is AlCl4 minus. So it is a nucleophile. So the proton is reacted towards this and it will eliminate. Then we will regain the structure. Addition reaction. There are several types of addition reaction. Addition of hydrogen, addition of halogen, combustion, etc. Addition of hydrogen. Benzene reaction with hydrogen in the presence of a catalyst such as nickel, platinum, etc. We required high temperature and under pressure. If we are adding hydrogen, we will get cyclohexane. Addition of halogen. If we add halogens in the presence of sunlight, we will get benzene hexachloride. If we are using bromine, benzene hexabromide. Combustion is adding of oxygen. On completely burning with oxygen, benzene gives carbon dioxide and water with the evolution of large amount of energy. When monosubstituted benzene is substituted to further substitution, 3 possible disubstituted products are not formed in equal amounts. 2 types of behavior are observed. Either ortho and para products or meta products is predominantly formed. This behavior depends on the nature of the substituent already present in the benzene ring. So, if we take a compound which already containing one functional group, for example chlorobenzene, and if we are further adding chlorination or if we are further conducting chlorination, where this substituent will add to the ring, which position, maybe ortho, maybe meta, maybe para, we cannot predict. But actually we can predict in these groups, some groups are ortho and para directing, next one is meta directing. So we'll see which product will be predominantly formed. Ortho and para directing groups. The groups which direct the incoming group to ortho and para position are called ortho and para directing groups. For example, OH. If already one OH group is present, the next OH group or next group will attach in the ortho or para position. Meta directing group. Nitro group, CN group, CHO group, COR group, acid group, esteric group, cyanide, thiocyanide group. These all are meta directing groups. Carcinogenicity and toxicity. Benzene and polynuclear hydrocarbon containing more than 2 benzene rings fused together are toxic and said to possess cancer producing. Cancer producing are known as carcinogenic. Such polynuclear hydrocarbons are formed in incomplete combustion of organic materials like tobacco, coal, petroleum, etc. And they enter to our human body and undergo various biochemical actions, and it will mute our DNA and cause cancer. These are carcinogenic compounds.